Hello, my name is Satvik, a student at Thomas Jefferson High School for Science and Technology. Along with my co-authors Jagadipra Madipatla, David Kao, Ryan Kim, and Stephen Liu, I'll be presenting using interferometer-based photonic integrated circuits to perform rapid unitary transformations. Now, a quick background. Our tasks are rooted in artificial intelligence, something that has greatly seen a large growth in the last decade, especially with the advent of generative AI and transformer networks. Unfortunately, traditional hardware that these large language models and neural networks run on are unable to keep up with heightened compute demands. For example, the cost to just train an artificial intelligence model doubles just tri-monthly. Traditional accelerators and microchips just require way too much electricity to operate functionally. Therefore, we need a new computing approach, one that isn't as rooted in the electrical means, one that is perhaps optical. See, we propose optical hardware that's completely energy efficient. Rather than using electrons in our circuitry, we use photons. We utilize photon based chips that expel minimal amounts of heat and run much faster at the speed of light. These optical computers that we've came up with are intrinsically faster than their digital electric alternatives. And specifically, in order to address the rapid growth of artificial intelligence, we introduce a specific matrix multiplication circuit, one we call a MATMUL circuit, has the potential to support the future of AI.
So with regard to the chip design, we kind of have two sectors. The first sector is the interferometer sector. So first we have an array of four lasers, which is represented by a 4x4 matrix, which can be represented by multiple 2x2 unitary matrix transformations. With regard to the interferometer itself, it's a Mach-Zehnder interferometer, 50-50 directional couplers as inputs and outputs, transmission coefficients tau 1 over rad 2, and coupling coefficient kappa 1 over rad 2. Below we have the relationship between the amplitudes going into and out of the interferometers, and below that we have the intensities, which vary with the amplitudes by square relationship. On the right side we have what is known as T, or the transfer function for each port, and that varies with the ratio between the input and output intensity, which also varies with the input and output amplitudes. So there's something to note there. At the bottom is some predefined variables that we didn't define above, but it's useful if you want to take a closer look. So the other part of chip design is the overall circuit. So say we're given an n by n matrix, we can represent that by n times n minus 1 over 2 number of 2x2 unitary matrices. So that's going to be representing as a whole an array of n lasers. So below that we have what it visually looks like. In the middle is a matrix. You kind of point out that Tij, which is what we have defined. In the middle of that is a 2x2 unitary matrix, and the multiplication of multiple of these Tij matrices will produce in our case U4, and U4 is the matrix that defines our circuit as a whole. And below you kind of see an image of what a circuit looks like, and also you see the relationship on the bottom left, which has something strange. It's called a Y splitter. The reason why we have a Y splitter is because we don't have enough grating couplers in the physical model, so we have to use the Y splitter. But don't worry, it doesn't affect the overall result, so we're fine there. And that'll be it for chip design.
Okay, now moving on to the chip implementation, we utilize a silicon wafer and optical components such as waveguides at the Applied Nanotools Foundry, also known as the ANT. And so we generated a transmission spectrum just to model the light intensity versus varying wavelengths. So on the y-axis here on the right, it's the proportion of light that transmits through the device. So it's essentially the efficiency of the device. So having a larger distance from the zero line or a higher absolute value of the ratio means that it is more efficient. And we found that optimal maximum light intensity to be around 1550 nanometers. On the bottom is the loss versus wavelength graph, and essentially loss quantifies how much of the light intensity is, well, lost due to the device, and having a lower loss is better. And the maximum loss is displayed in around 1520 to 1540 nanometers. So for testing, the chip was fabricated using just a standard CMOS manufacturing process at the Ant, and an SOI thickness of 220 nanometers and a silicon dioxide thickness of 3 microns was used. And after manufacturing and cleaning and using a resist, the chip was tested at the University of British Columbia. And this was done using a series of laser pulses ranging from around 1480 to 1560, 1570 nanometers that were actually transmitted through the chip. And to visually analyze this, we use scanning electron microscopy, and it's actually shown on the right. And we took in several performance metrics, such as clock speed, performance per watt, and just performance to compare our 4x4 fabricated chip and 256 by 256 scaled up chip. And the results can be seen on the bottom right. And what we actually found using instructions of 1 MVM per cycle, we found that our 4x4 had a much higher clock speed, as it should, because it's lower dimensions, but it actually does worse in performance per watt and general performance, which means that our device can be scaled up for high dimension learning.
Okay, so now on to the conclusion and discussion of the paper. Throughout this paper, we show that it is possible to create an optical silicon photonics-based chip catered to perform matrix vector multiplications. Furthermore, we developed a silicon implementation of this chip on a silicon wafer through the aforementioned A&T fabrication facility in conjunction with the University of British Columbia, or UBC. And furthermore, we've tested and verified this chip with various signal loss testing measures and procedures through optical probe stations at the aforementioned A&T facility and the University of British Columbia. The chip is extremely significant for the future of AI, particularly because of 3 reasons. Firstly, we see an independence from traditional transistors. Since the chip itself is analog in protocol, if optimization were desired, the chip itself can be optimized without the need to worry for quantum tunneling, which is often the case when individuals try to decrease the size of transistors. Furthermore, there's a dramatic speed boost that is provided inherently by the photonic architecture, since the speed of light is intrinsically faster than the speed of electricity. And traditional digital electronic devices, such as GPUs and TPUs, which currently power the AI industry, those are dependent on a digital protocol based on electricity. And as such, our photonics chip it will be able to outperform traditional digital electronic devices with respect to speed. And furthermore, there's a dramatic energy efficiency that's also provided, since there is no resistance that is encountered when photons interact in the waveguide of the silicon chip. The use cases are profound as well. For example, in autonomous vehicles where speed of inference is of the essence, and where there's very limited electricity and power stored in the on-car batteries, energy efficiency and light speed inference will be very welcomed. Furthermore, the transistor architecture, which is a type of AI model used for generative AI and LLMs, the transistor architecture has grown exponentially over the last 2 years, and it is also very computationally intensive to do forward passes on and to train. Traditionally, to train the transformer architecture, many companies such as OpenAI and Facebook have resorted to purchasing large clusters of GPUs and TPUs, which consume vast amounts of electricity and take months to perform training. As such, points 2 and 3 that are listed on the slide that are proponents for the chip will be able to help with the processing of transformer models. Lastly, in the field of robotics, where software is growing exponentially and where companies such as Boston Dynamics are consistently attempting to make better robots, on-board chips to perform inference and AI calculations at the speed of light will be welcomed as well. Thank you for listening to our presentation.